Hi, as you know, I'm Chris Harris. I'm on Project 14, which is about decision making. So today I'm going to talk to you a little bit about creating statistics, which sounds a bit like an oxymoron, doesn't it? I have to say, I'm pretty impressed with you guys. Not only CogNovians, they're new thinkers. But actually, a really clever lot, I have to say. You walk through that thing and you feel this intellectual atmosphere. Carve your way through it. It's humbling. And I'm talking last night, quite a few of you. You know a lot of stuff, right? I can see that. And I'm really humiliated if I don't know this stuff. I know how to do certain things, but I don't know about stuff. And you've done lots about stuff because you've got degrees in this, that, and the other, and you're just full of all the stuff you've been taught, aren't you? Well, part of the talk today is to try and unstuff you a bit. Don't get me wrong, knowing stuff is good, but it's where you put it in your mind that's the bit I'm trying to get at. So, are you being framed, as you can probably guess? If you're a psychology background, you probably know where I'm coming from. So my talk today is going to be 2 hours. Sorry. First hour, well, I don't know how it's going to go. I've never done this before. So the first bit is about thinking, how you think. Now, I'm not prescribing how you think or how you don't think. What I want you to think about is how you think. And that's the bit I'm trying to get across first bit. And then I'm going to give you some examples from stuff that we've done, which actually led to Project 14. And that's the content. It doesn't matter what it's about, it's the way we do it. That's what I really want to get across. In fact, any of my colleagues could give you loads of examples of how you think about doing experiments and kind of things you can find out. So that's what the idea is. So you're all here now, you're all coming all over the place, and you've unpacked everything. Now you've got to unpack your brain, right? And that's what I want to talk about. Which means, of course, I know it's a hackneyed phrase, but I don't know how to think out of the box, that's what I'm trying to say. And that's not easy. It's not easy to think outside the box, because you don't know which box you're in, right? How many of you are psychologists by your first degree? Okay, quite a few. Well, guess that. How many of you computer programmers? Right. Cool, we've got competition on that, haven't we? And so, how you think about things depends on your background, of course. If you're a psychologist, you love SPSS or whatever program, you can press buttons and do maths and variance and quicker than I could ever think about it. If you're programming, you can probably program 20 languages, and most of you can speak about 20 languages as well. So, and of course, you learnt all that, and then you got degrees for it, and that's really, and you're rightly very proud of all that. So what I really want to try and get across is, you don't want to forget any of this stuff you've learned. That stuff, all right? It's all like literature and what you've done. Just stick it away in the corner, just in case you need it. And that, you think about the bigger picture, which is a problem every director of studies or of a PhD student knows absolutely full well the biggest problem is getting their very, very clever students to think the bigger picture, and they don't. And I call it BPP, which is a clinical condition. It's not yet in the psychology DSM-4, but it means big picture blindness, right? Not seeing the bigger picture because of all that stuff you've got. And on one, particularly programs, really it's a real problem. Because when you program, you have to use all your brain to think how to program. You can't, well I can't. I can program a bit. I try not to, because it absorbs all my thought process. You can't drink wine and program, it doesn't work. I tried. Programs never work, but and it's hyperactive I call it hyperactive attention to detail. Now, it's a good thing you've been taught to be attentive to detail, but you can overdo it. So what you need to do is think, right, a switch in your mind. I'm going to be attention to detail now. That's what you do. And then you don't. You switch it on and off. It's not your life. So, which is hard for those with OCD, but that's what you have to do. So, this is absolute rubbish, but never mind, it's just illustrated. It's a metaphor. You've all heard about this, right? Left brain, right brain. Well, of course, it doesn't work like that at all, really. But the idea is that you have a lot of faculties, and you're all very clever, we know that, we interviewed you, right? And so you need to use all of your brain, not just the psychology bit, but just the programming bit, or the philosophical bit that you have. And you really need to use your corpus callosum. Okay? It's a really important part of your brain. And I think there are people with HSS corpus callosum. I don't think any of you, but you do need to use it. So think about why you're thinking about it. Now, there's another condition. This is the psychological condition. This is equally invidious and insidious. Hyperactive hypothesis testing. And it's a hard one. I mean, hyperactive attention to detail, you can switch off if you use it. This one's really, really tricky, particularly for psychologists. Because you've been trained to test hypotheses, P.05, etc., etc., etc. All right? Well, I can't remember the last time I did hypothesis testing, but it's a problem. And that's what this talk really about, this first part. So, before you can do any hypothesis testing, you need something to test. But where does that come from? Now, is it going to come from you, your mind, or from the stuff you've got stuffed in your brain? Most of the time it comes from the stuff you already have there. Right? I'm going to test Blogs' theory of attention deficit, and we'll come up with something. My null hypothesis, my alternative hypothesis, etc., and off you go. And you don't actually think about the situation before you get to hypothesis testing. Now, I'm going to talk about the tyranny of hypothesis testing. Me and Chris are going to talk to you about that next workshop. All right? This workshop, I'm going to talk about this bit of top, the thing that should come before hypothesis. But it doesn't. Because even though I say, right, go away and think about something, when you start designing your experiments, you start thinking about how am I going to test? How am I going to construct the hypothesis test? It's ingrained in you for years. Right? That's the problem. You start thinking about testability and philosophical ones of you, or think of logical positivism, and Popperism, and thiserism, and thaterism, and how can I get to it? How can I prove this hypothesis to be true, etc. And that whole thing is the edifice, as I call it, of inferential statistics. Now, a bit of a digression. When I started out in physics. I've done a lot of things since then, but I did physics, and went to London, and I went off, did optics, I did all sorts of stuff. And then I got fed up of being in Britain, and I went to New York. So I started a PhD in something called experimental psychology. No idea what it was. It's a great way of getting a visa to live in New York. Anyway, what I didn't realise was that to pay for that, I had to teach. And I left in August. My first lesson was in September, about a week after I landed. And I had to teach statistics. Which I thought, hey, it's no problem, I can do maths, I'm not a physicist. And then I had to teach inferential statistics. I haven't got a clue what that meant. How can you, now I'm thinking back, I must be naive, but actually, I think I'm glad I was naive, because inferential statistics is all about making decisions, of truth in that. And actually, that's not how you do science, in my opinion. So I was very shocked. I had to, I bet, one lecture ahead of my students. And the problem is, and this is just an illustration, any statistic you come up with is based on this, is the idea is that you're taught, right from day one, that you need to do a C test, right? Or a no F test, or this test, or that test. And you've got to look at the difference between the two groups, that's what you're doing, and you divide by your standard error, and you come up with a standardized effect size. That effect size is bigger than 1.96 or whatever it is. Hey, great, alpha 0.05 is true. Well, you know that's not really true, but that's what the goal is. And then you publish papers, become famous, and carry on doing it for your life. Right. And the point is that the standard error depends on n. And n is the number of samples you have, the number of people you manage to recruit into your study. That's what you're kind of thing of doing. And then, of course, the more people you get, the bigger this number gets, the bigger the T gets, the bigger the probability of getting rejecting the hypothesis, and that's what it is. But of course, that's just another absolute poppycock. Because nature out there doesn't care about what you're doing. You're looking at an effect, it's something that's different between your two groups. What you really want to do is, you don't want it. It doesn't matter about standardizing. What really matters is the true effect size. I know it's page 1 on your textbook that you started with, but it is the most fundamental misconception I can think of, really. If the world, if you have two groups and they are different, that's what you're interested in. All this does is tell you how reliable that number is. That doesn't mean you don't do this, don't get me wrong. But what's really important is the actual effect. And you know, because most of you got second degrees as well, you know that if I had a correlation coefficient and it's, 1,000 people, I could get a correlation coefficient that's significant, right? Great. And the correlation coefficient is 0.01. R is 0.01. Well, of course it's significant because you've got 1,000 people, but it means nothing. Same for t-tests. And it's embarrassing for me too, because I have to lecture for their final year psychology students, and I lecture on experimental research design, and I go into power analysis and doing all this stuff, knowing full well that it's nothing to do with reality, that's reality. That's just experimental technique. Right? So you see, that's not the only problem. You probably don't realise it, but you're making all sorts of assumptions. Anyone does stochastic analysis here? Anyone does stochastic theories? Okay, right. I won't test you. But there are some huge hidden assumptions whenever you do all your statistics. One of them, of course, is that it's stationary. The statistic doesn't change with time, which who knows. If that was the case, you'd never learn anything, right? So that can't be really true. You are drummed into you about independence, that your samples are independent or your measurements are independent. Well, they might be, they usually not. And ergodicity, ever heard of ergodicity? Something you don't know. Stuff that is, it's good stuff. Ergodicity is the fact that if I measure you, and then that you would all do the same thing, statistically speaking. Of course, this is not true. But the trick, of course, is I'll take your mean, standard deviation, your mean, and I'll standardize you, and then you're all the same. Right? That's making it all ergodic. Well, I'll get to this. I'll give you an example of where that's wrong. But that's the general idea. That's what ergodicity is. So, So the problem is, if the world really was stationary and independent sums and ergodic, it would be a very, very boring world. There'd be nothing to find out. So, think about it. We make all these assumptions to do these statistical tests to find out something new. Yet, by doing so, we've made everything the same. So we assume it's the same, so we can do the test and see if they're different. It's not really Don't get me wrong, it's mathematically perfect, correct. I'm not in mathematics. It's just, I wonder what you're trying to find out. Anyway, we'll come back to that. There's another disorder, which is viable, which is metaphor susceptibility. And talking about it yesterday, I could see that everybody's got problems. We all do. We love metaphors. We humans love it. And I'm going to upset the artists here. I have to say, I'm not an artist, not at all. When I was undergraduate, everybody had Dali on your wall posting on it. It was cool. No one understood it, but it was really cool. And it's called surrealism, which is a really cool word as well, right? But anyway, this is one of his pictures. And of course, it's a metaphor. And artists love metaphors. Right? In fact, they live off metaphors, I think. You know, if I can twist it this way so it looks something different, then that's good. I call it money. Publishing. So my paintings or something. Personally, I'm not a lover of metaphors in art. Once I get it, it's like an old joke, isn't it? It's a bit corny. But nevertheless, you do need some kind of metaphors. And I think I've been talking to you already. There's big metaphors of one kind or another. So, but it's a trap. Now, this is no insult to art. If you want to use metaphors, absolutely fine. But when you come to do science, metaphors are a disaster. And I'm going to show you some examples. This is a quote from Emmanuel Domer, who's a famous book writer, economist, mathematician. And he wrote this. Theories, I'll read it out because it's absolutely perfect. Theories deal with the world by its own terms. Absolutely. All right? Models are metaphors. Relative descriptions of the object of their attention that compare it to something similar already better understood in theories. Models are reductions of dimensionality, it's a nice thing as well, that always simplify and sweep the dirt under. And we all do it, get some results you don't like. Well, ignore it. Don't put it in the figure, right? Theories tell you what something is. Models tell you what something partially right. And that is really, really absolutely fundamental. I didn't know that Einstein discovered this a little while ago, because I don't fill my brain full of stuff, so I don't read books. But that says it all. And I'm going to give you an example. Because, now this is a twist to this. I know I did physics, I'm going to give you a physics example. But we're going to come back to this. There's more to this in detail. This is, let's roll back the clock. 1910, 5? Oh, turn of the century, 1900s. If you did physics and you try and understand how matter was in those days, this is the model everyone had. It's a classic model of, this is your nucleus, this is your electron. It looks like a planet going around a star, and that was the nearest metaphor we had in those days. Instead of gravity, you've got electrostatic forces, so electron is attracted towards this nucleus, but it spins around, which chucks it out, so it just balances right? Everybody thought that's how the world was, how matter was. Even Rutherford thought it. So, and of course, everybody who was at universities and doing physics or at school, you saw teachers metaphor. Everyone knew it was wrong. The reason it's wrong is because when an electron whizzes around, it's accelerating, and we know charged particles accelerate, they're going to emit energy, and they go to eventually it's going to collapse into the nucleus. And that whole world just collapsed into nothing. So, never mind, that's just physics. But the point is, everybody knew it was wrong. So, but no one knew what else to do. So, the whole of physics community was trapped in a matter. Why on earth would the nucleus of an atom be anything like a solar system? Why on earth do you get that after ideas? So along comes some really famous, clever people. It was Bohr being the first one, of course, but loads and loads of really clever people. And said, well, screw that, we don't want that at all. I reckon it's something to do with the quantum theory. Energy comes in packets, and as long as it stays, and if it loses or gains energy, it's going to jump in and out of orbit. No one knew why that would be. But it seemed to make sense, and you get some really nice results from that idea. It seemed to match reality, like hydrogen lines and things like that. Anyway, so that was a seed for a new, completely new idea, which we now know to be quantum theory. But it left a real problem for those physicists. And if you read their history, it really was a big problem. Because then de Broglie comes along and talks about waves and particles, and it all seems to work, but it means these photons or these electrons can be waves, or they can be particles. Sometimes they're like one, sometimes they're like the other. You can't be both, can it? So the literature is absolutely replete with examples of tussling with this problem. It's quite remarkable. You should read it. So the problem was, of course, the real problem was stuff. Is that people really needed a metaphor. It has to be like something. It can be like a particle, or it can be like a wave, but it can't be both. Why not? But anyway, and that's the problem. We love metaphors. Okay, get the idea of what a metaphor is? And it's a serious problem. Okay, let's change the subject. Let's go into history of psychology, I suppose. I don't know what to call it. But this is Descartes' view of the brain. I call this humanoidism. So the brain was full of pipes and fluid and so on. Of course, in those days, in the 1600s and whatever, that was the latest technology. Right? Pipes, they could pump water around cities. Right? So it makes sense to think of the brain as the most advanced thing we have. So it's full of pipes, pumping around liquid. And somehow that means you can think. So, cognitive pipes. Anyway, no one had a better idea, and no one could do much with it. People had brain problems anyway, so it just stuck around for a few hundred years. It's a long time. Whoops. Until the modern era. Then we started thinking about how brains really work. Whoops, I think I skipped something. I have skipped. So I have to make improvise. So then what happened was people started thinking about, excuse me a minute. Oh yes, it is there. So then people, so we live in the modern era, and I spent some even doing some of this, computer and human interfaces and that. And then we'd like to think of the brain in a metaphorical way. Well, we don't know often know we're doing it. But this is one approach. When I did physics, back all those years ago, I took the third year option, which was to do electromagnetic theory, which was a completely masochistic thing to do. But I got to learn about electronics and systems theory and everything, which you didn't do. And I was taught we have this feedback systems that the human closed the loop. So, and that's how engineers used to think about it, still do something. So, for example, here's a vehicle, car, helicopter, plane. This is the human, right? You look out the window and you predict what you're going to do and feedback and control. Right? Mona can tell us all about that because she flies aeroplanes. And you've got to get it right, really, haven't you?
Yes, I hope so.
So basically, that's what happens. Of course, it looks good. It doesn't work too often. Well, it works quite a lot of the time, but it goes wrong, doesn't it? We know about it. I have to lecture to aerospace engineers. And I've given lectures on why humans make errors and why they keep flying their airplanes into the sea and things like that. It's because they're not machines, they're humans. So they find that really hard to understand. But this is one that really gets me. That's up to date. Blueprint for an artificial brain, right? The artificial brain's electronic circuit. You can do it, you can imprint it in VLSI technology, and you can plug a human into something, right? This is, what is this? Anyway, so, how much effort has been spent trying to capture the essence of human and stick it into a circuit. I mean, it's phenomenal. And of course, the really strange thing is we as neuroscientists and psychologists and that, we don't know how the brain works. So how are they going to do good shit? This is the male version. This is based on me. Right? So, but the real problem is the computer metaphor. Right. Back in 1960s and 70s, this famous guy called Alan Turing, you've heard of him, he's been in the news again recently. And he wasn't just him, but lots of people invented computers. I don't know, I mean, you're all so young. I can remember life before computers. There was no such thing as software. It didn't exist. What a bizarre concept. And when it did exist, you had to toggle in the code into a piece of paper tape with a hole in the right place. And it didn't work, you made a hole in the right place, so it did work. And you read it in, and you code this thing to move binary numbers from one register to another, and so on. And you could jump back, go into loops are pretty loud. It goes on and on and on. And it does really complex things. And that's pretty impressive. If you've ever done it for the first time, it's absolutely really brilliant. So, you can get complex behavior out of this machine from a very simple set of instructions well, registers in those days. And of course, it struck everyone, including Alan Turing, that maybe we could generate human-like behavior from these machines, hence Turing machine. And we're still at it, but that was 60s and 70s. Hey, you know what? Yeah, maybe the brain is like a computer. A bit like pipes from Lego, right? It's the most fantastic thing we've ever made, a computer. Even in those days, it was fantastic. So, hey, I reckon the brain's like that. Yeah, wonderful metaphor, right? We still use the same phrases, processing time, circuits, this, that, and the other. It's all based on these metaphors, right? And then, well, of course, when computers have full of software, maybe human behavior can be seen as software, right? And so, of course, if it is software, you can do psychological experiments to understand this software, which we call cognitive psychology. It didn't exist before the 70s, it was all animal behaviorism. You couldn't look inside these boxes. You weren't allowed. But famous psychologists like Rice and that said, yes, you can. And the whole computer metaphor emerged. And then, of course, the irony is yet to come. Hey, if we can get this software out of your head, we can stick it in a machine and make robots that are humanoid. And it's quite fantastic, yeah?
So which projects are you proposing to cancel here?
But what's ironic is that I work with a lot of people and psychologists and neuroscientists and all, so I'm not particularly having access to it, but I can't help notice that the roboticists say, can we get a psychologist on board? Because our robots all they can do is not walk into walls. We want them to do something. Let's get the psychologist. And because what they don't realise is the psychologists they get on board, they're the ones that have been trained with a metaphor from the engineers back in 1970. So it's recycling metaphors, basically. And that's where we are today. So we call it different words, but same idea. Now I'm going to show you this. This is a true story. This is a paper published in 1983 by Patrick Suppers et al. He was a very famous cognitive psychologist and a mathematical psychologist. You may not have heard of him. I certainly did, so I'll explain this. Here's a paper, I should say I study eye movements, right? Here, and that's why I know this paper. This is how you do a rhythm. He's serious, I should say. In your brain, you have this code, And you go down this code, you call up subroutines when you do something that's common, and then you come back and go on and on and on. He published this in the Journal of Mathematical Psychology, which is a pretty good journal, especially in those days. Still is, really. And that's how they thought the brain worked. This is not a metaphor, it is a metaphor, but they don't see it as a metaphor. All right, so if you saw that today, you would laugh your head. You'd be embarrassed to even have your name on it, right? I think it's down now. But the reason I'm bringing this up is because it irked me enormously, because I just could not believe this stuff, right? It was like absurd. Everybody had been publishing procedural models of little subroutines, usually in Fortran, just shows how old it is. But today it would be object programming of some kind or other. And that's really in your head. So I tried to publish a paper on how you move your eyes, and went to send it off to Vision Research, which was a pretty good journal in those days, not so good anymore. But on non-cognitive stochastic modeling of how you move your eyes. It was non-cognitive in the sense that it wasn't this kind of thing. This is cognitive psychology. And actually I sent two papers. One was basic phenomenology, which got accepted. The one with a model got rejected. He was the reviewer. And then I applied for a job in Nevada. That's when I was in America. Nevada's a beautiful place, by the way. Anyway, I applied for this job. I got all the way through to the final thing, but I didn't realise the guy who was making the final decision was a very famous psychologist called Bob Salso. I think he's also dead now. And he was famous for this kind of stuff. I didn't get the job. So metaphors are funny maybe, but it changed my career completely because I didn't believe in that metaphor, yet they did. So it's for me it's quite a poignant thing, but I still look at this, I still can't believe it. Now, something a bit more modern. We're going to make decision makers curdle. The metaphor of classical probability, Bayesian reasoning. Who hasn't heard of Bayesian reasoning? Hasn't. You're lucky. You're lucky. Don't fill your brain with this stuff, right? Better you try and unload it if you can. Including Chris. So, Bayesian reasoning is well, basically it comes from Bayesian, which is probability, it's mathematics, it's truism, it's just mathematics. But pretty much most neuroscientists today believe our brains are Bayesian machines. I say that I know because I've talked to lots of them. So my colleagues are the best Bayesian reasoners in the world. And impressive. And you can always make it fit your data. That's the beauty about Bayesian reasoning. Because of priors. You can always come up with some priors that fit what you want. Okay, so I'm going to do some equations there, all right? Do not worry. Here's the fundamental rule of probability, condition of probability. The probability of getting event A and B happening is given by the probability of A happening given B times the probability of B happened. All right? Standard stuff. And that's probabilities. That's fundamental axiom of probability. Because the other way around to that, probability of B and A happening flips around. Obviously, probability of A and B and A are the same thing. So those two things are the same. So you end up with the probability of A given B is equal to this thing, which is Bayes' rule. And that's where it all starts. That's the whole beginnings of Bayesian reasoning. So, for example, if this is the probability of hypothesis H1, given evidence you got from the experiment, it's given the probability of getting that evidence given some hypothesis times the rest of it. And that's the origins of decision, hypothesis testing, everything revolves around that. And of course, can't argue with it, it's true. But if, and only if, there's the two estimates, if that's true, right? Is that true? Of course it's true. If I give you What's probably getting, ace of spades and a queen of hearts, it's the same as getting, probably as getting a queen of hearts and an ace of spades. Doesn't matter. Except when you come to humans. This is a slight little niggling problem. When we make decisions in time, we make them in time, right? One after the other. I suppose you don't have to, but we do. And most of the experiments we ever look at do require you to make a decision, then another, and so on. So, now, back to quantum physics, just for a second. That sounds reasonable, but that's not how the physical world works. We know that probability of A and B happening is not the same as probability of B and A happening, always. And that's called non-commutative, physically called it non-commutation of operators. It depends on the order in which you do things. Now, I don't know if you know this, but there's an emerging area of quantum cognition. I don't mean quantum computing, don't get mixed up. Quantum cognition, which says this is not true. And can read all about it. You look it up. And basically, it's called non-compatibility. So if I asked you, if I asked you, I like cats. So if I said, do you like cats? And you do like cats, because you've got a lovely, fluffy pet cat. And I say, do you like cats? And you say, yes. Are you happy? You say, yes, because I'm thinking of cats, right? If I say, are you happy? No, I'm not sure. Do you like cats? Yeah, I like cats. It's not the same thing, obviously. There's hundreds of examples, I just can't think of one. And the point is, it doesn't work. That means Bayes' rule is wrong. Sorry, it's not wrong. It's a metaphor. We don't think like that. We think like we think. There's no metaphor for it. Not yet, anyway. Oh yes, so here. Talk about cats. Yes, you all know it's Schrodinger's cat, right? So if you make an observation on some particle, if it's there, cat dies, it's not there, it stays alive. So something's wrong, because it can't be dead and alive. Because in quantum theory, you don't know what it is. It's somewhere in between. It's probabilistic until you make a measurement. So it's a bit like me saying, do you like cats? You actually never thought of it. Question, so I asked the question. Suddenly I put your brain in a different state. And it's a bit like I force it into a state, and then the cat dies. So that's the idea. So it's a hypothetical Gedanken experiment. That's the subject of so many textbooks. It's amazing. But it illustrates the point. So, metaphors. You need to think about what metaphor you're in today. All right? Now, I've got... we're doing all right. Here's my hero. This is, does anyone know who he is? Richard Feynman. Yeah, Richard Feynman. The cleverest guy you ever met. I never met him. Back to physics. He's a physicist. He's famous. He got the Nobel Prize. He sorted out the Challenger when it blew up by the O-ring business. He did everything. He could unpick lots. He played the bongo. He did everything. He's one of those amazing people.
He was on the Manhattan Project as well.
He was on the Manhattan Project. Thank you. So, and more to the point, he wrote the lecture series that we studied when we did physics, right? So that's what everyone knows from. And he's a very clever guy. So I'm going to leave him. So let's see what he says. He's going to talk about this nutty problem of the duality, right? Now I know we're not doing physics here, but it's very illustrative of the problem. And this guy is so clever. And he's so clever because he has no stuff in his head. He carries no baggage around. He just asks, he's like a kitten. He asks these crazy, silly questions, which no one ever thought to ask, because they're all too busy, full of stuff. And let's see if I hope this works. I hope the sound works too, so it goes on for a few minutes.
Oh, that little thing behaved very differently than anything that was big. Anything that you're familiar with. Because you see, as the animal evolves and so on, its brain evolves, it gets used to handling the brain is designed for ordinary circumstances. But if the gut particles and the deep inner workings were by some other rules and some other character, they behaved differently, they were very different than anything on a large scale, then there would be some kind of difficulty in understanding and imagining reality. And that difficulty we are in. The behavior of things on a small scale is so fantastic. It's so wonderfully different, so marvelously different than anything that behaves on a large scale. You say electrons act like waves. No, they don't exactly. They act like particles. No, they don't exactly. They act like a kind of a fog around the nucleus. No, they don't exactly. And if you would like to get a clear, sharp picture of an atom, so that you can tell exactly how it's going to behave correctly, another good image, in other words, a really good image of reality, I don't know how to do it. Because that image has to be mathematical. We have a mathematical expression, strange mathematical, I don't understand how it is, but we can write mathematical expressions and calculate what the thing is going to do without actually being able to picture it. It would be something like a computer that you put certain numbers in and you have a formula for what time the car will arrive at different destinations, and the thing does the arithmetic to figure out what time the car arrives at the different destinations, but cannot picture the car. It's just doing the arithmetic. So we know how to do the arithmetic, but we cannot picture the car. It's not 100% because for certain approximate situations, a certain kind of approximate picture works. That is simply a fog around the nucleus that when you squeeze it, it repels you. Is very good for understanding the stiffness of material. That it's a wave which does this and that is very good for some other phenomenon. All right? So when you're working with certain particular aspects of behavior of atoms, for instance, when I was talking about temperature and so forth, that they're just little balls is good enough, and it gives a very nice picture of temperature. But if you ask more specific questions, and you get down to questions like, how is it that when you cool helium down, even to absolute zero, where there's not supposed to be any motion, it's a perfect fluid that hasn't any viscosity, has no resistance, flows perfectly, and isn't freezing? Well, if you want to get a picture of atoms that has all of that in it, I can't do it. But I can explain why the helium behaves as it does by taking my equations and showing the consequences of them is that the helium will behave as it's observed to behave. So we know we have the theory right, but we haven't got the pictures that we're going through. And is that because we're limited, have we caught on to the right pictures? Or is that because there aren't any right pictures for people who have to make pictures out of things that are familiar to them? Well, I suppose it's the last one. If there's no right pictures in terms of things that are familiar to them. Is it possible then to develop a familiarity with those things that are not familiar on hand by studying? By learning about the properties of atoms and quantum mechanics, by practicing with the equations, until it becomes a kind of second nature. Just like it's second nature to know that if two balls come toward each other, they smash into bits. You don't say the two balls, when they come toward each other, turn blue. You know what they do. So the question is whether you could get to know what things do without, better than we do today. As the generations develop, will they invent ways of teaching in a way so that the new people will learn the tricky ways of looking at things and be so trained, so well trained, that they won't have our trouble with the atoms of picture. There's still a school of thought that cannot believe that the atomic behavior is so different than large-scale behavior. I think that's a deep prejudice. It's a prejudice of being so used to large-scale behavior. And they're always seeking to find the way for the day that we discover that underneath the quantum mechanics, there's some mundane, ordinary balls hitting or particles moving aside. I think they're going to be defeated. I think nature's imagination is so much greater than man's, she's never going to let us relax.
Well, that says it all. It's brilliant. So, got to break in 2 seconds. You've got lots of stuff in your range. You've got lots of skills, lots of ways out. keep them. They're very useful things to do. But don't turn them into metaphors, all right? So if you want to learn math, lab's great. It's a good thing for solving problems. Maths is great. I never try not to open metaphors. I'll do it in this one, So that's what I want you to do. So, because we've got to be CogNovo, not CogPaleo, right? So let's have a break from it, then I'm going to talk about some nitty-gritty things. So when you think about it, now that you think about these things, when you do an experiment, what are you doing? Well, there's the world out there. You hope you're not interfering with it too much by doing the experiment. You want too much awful effects. So you're trying to measure the world, whether it's in there, out there, whatever. And you're trying to get some information out of this procedure of the experiment. And you want to be able to see what you've got. That's the whole point, really. You can't see quarks or electrons. You can see electrons. But the point is, you have to make some experiment to try and find out the effects of that, whatever's out there. You can be translated to you, so you can visualize it in your head. If you couldn't do that, there would be no point in doing an experiment. And really, you think about it, that's what an experiment really is. And then you try and put it to your head and with other experiments trying to come up with some hypothesis, which you'll test without for 0.05. But the point is that what you're really doing is making a transformation of stuff out there, the world, into some mental representation that you can understand and you can share with each other. And that's what I'd like to talk about. So I'm going to show you some examples of work I've done recently to kind of illustrate that point, but in doing so we should also refer back to some of the points I've already made. Have you ever seen this stuff, anyone? Yeah. Actually, yeah. Right. So here's a drawing on the road. This is I got off the internet, and everyone's crammed around looking at it. We're not standing this end of it at all, actually. But when you get the right perspective, you look from the right direction, this is a metaphor, it all stands out very clearly. And that's what we're trying to do with experiments. Is fiddle around with the data or the experiment or, when it comes along, you can see things. Before that, it's just noise. So, I'm going to give you 3 examples. And you don't have to worry about the content there too much. That's not what the point is. The point is what we've done to the data. I'm going to talk about optokinetic nystagmus. I'll explain that in a second. Reaction times, gain theory. Now, I have to make, before I start, I just have to say that for me to make sense, this all makes sense, I don't think about it as systems 1 and 2 and things, all that stuff. It's just about brains, right? So when I talk to Christopher, it's my brain talks to his brain. We're not people. I know we are, but that's just a confabulation that we make, right? The point is, it's brains communicating with each other, and it's brains that make decisions. And that's that's a subtext of what I'm trying to do. That's just a peculiar way of thinking about it. So optokinetic nystagmus is a low level. For me, low level. But what you're right. So here, let's hope all this works. So here's I should say I also work at the hospital because I'm an eye movement person. I study abnormal eye movements for the ophthalmology department and for the neurology department. So when I'm looking at your eye movements, I can look into your soul and tell you if you've got problems in the brain, right? And sometimes it works and you can make diagnosis and things like that. That's a whole different part of the toolkit. But, whoops. So here's a young man with pathological nystagmus. Just watch. Can you see? You can see at least his right eye. See? Can you see what's going on? Can you see the back? His eyes are what? All the time. The only way we stop those eyes from wobbling is to inject him with phenobarbital and knock him out. He has it all the time. And so that's why I'm quite interested in, it's called nystagmus, it just means it's a Greek word meaning, actually it means like what you guys do, is your head falls in, you're trying to pay attention, you can't. But actually it's being used for eye movements. And he has abnormal eyes. I haven't seen any abnormal eyes. I believe I've checked all of it. You don't know it, but I have checked it. And so the question is, he could have a brain tumor or everything, but he doesn't. He was born with it. And we haven't got a clue. We really honestly can tell you, we don't know. We can't cure it. We don't know why he's got it. What's making it happen. I could give you 5-hour lecture on all that, but I'll spare you that. But the point is, it's what provokes me is trying to understand what's going on. He doesn't fit any, and 1 in 1,000 people get this, they don't fit the cybernetic metaphor. I remember I showed that cybernetic metaphor. Historically, the study of eye movements has all been about cybernetic metaphor, feedback systems and stuff like that. And so this is a real problem because it cannot be explained by it. It's a bit like the atom and the electron. You know. We know it's not right, we know the metaphor is wrong, so what is going on? And so I've started, been doing this for a while, so I'm trying to look into why. So rather than looking at him, because can't do much about it, he's got it all the time. We can look at his DNA, we can find things, but it doesn't explain why he's got it. If you look, we can record his eye movements, and we can look at these waveforms, the oscillation of the eyes, and I can, because I've done it so many times, I can tell you straight away what kind of nystagmus. I can say, hey, he hasn't got a brain tumor, he was born with it. And what we look at, so we get to nitty-gritty here. So what we're looking at here is the red bits are saccadic eye movements, the flicks you will make, and the other bit is something bizarre. So we call the saccadic bit, this is high-level technology, it's called quick phase, and the other bits are called a slow phase. See, I told you it's sophisticated. And by looking at that, we can do lots of medical stuff and send them home without a cure. But it's what we can do. Should I use this stuff? It never works. Come on. Yeah, there we go. We can do this to you guys. Right? If you all look at that, you're too far away from it, but I know it's flickering. Forget the flickering. If you just look at that, everyone look. And you can look at your neighbour. Your eyes are all doing this. You don't know it's happening, but it is happening. Check. If you look in the middle, sorry, you look at. Don't look at yellow.
We're too far away.
If you don't have it, come and see me later. I'll do some tests. This is quite interesting. Before I go, I'm just going to have a quick digression. That young man you just saw, was nystagmus. Do you think his eyes are doing that?
It's a very small between
Morning. Hello. You'd think that when his eyes are doing that, you would see the world, he would see the world moving, which is called oscillopsia. He doesn't see the world moving. Right? Now, if you and I got nystagmus, we would, and we'd be down having a brain scan instantly. But he doesn't, he's had it all his life. Not quite sure why, got some ideas. And you think, oh, it's because he's baby and got adapted to it. If we build an equipment and move, so when he looks at a target, and we stabilise it on his retina, so when his eye moves, the target moves just the right way, we can do that. And then, of course, it's stable on his retina, you think that would be fine, wouldn't it? He doesn't, he sees it moving. I'm not going to tell you why. But, I'm not going to tell you. So it's something to do with his brain, right? Anyway, so when you see that, if we had a big one, and you couldn't see the rest of the world, and the more you could see it moving, you wouldn't see it moving. You'd think that you were moving. It's a very strong, it's called vections, a very strong sensation that you're moving. I used to have a big curtain of the motor in the ceiling, stick the patient there or anyone in there and move it around. I used to stand in there to hold them head because there's lots of kids. And as the curtain goes around, at first you start following it, and then you think, wow, and I'm whizzing around the opposite direction. So this most amazing thing. Nevertheless, when you look at the eye movements, they're doing this, right? So this is what we were looking at. I can't stop it. So here's my follow PhD student, Jonathan, who we recorded eye movements, and we're looking into, what we're really looking into is what I call decision making. You probably wouldn't, is that somewhere along those waveforms, when you follow it, you make a saccade. Why do you make a saccade at that time? No idea, but it can't help but help us understand what's going on with that young man. And so we can record it, here it is. It's like rubbish, but if you look closely, you get, this is the recording you get when the world, if we recorded your eye movements, you do the same. You follow, then you reset, and that's slow phase and that's quick phase. At some point, you can see it's quite variable, at some point you make a quick phase. Your brain makes a saccade. Now we know the whole circuitry of saccadic movements, absolutely, down to neurons. We know how it works, we just don't know what makes it happen at a certain time. So it's not a lack of, not a lack of physiological understanding, but why does it happen when it happens? So that's what we're looking at. And that's the slow phases, and that's the quick phases. So now, well, I'm not the first to have done booking. I mean, it's been going around since the 60s and 70s. And you think, well, what's new? Well, this is where metaphors go in. The metaphor, or the way people have thought about this since the 1960s and 70s, is that this is a reflexive behavior, that when the world moves, you follow it, keep the image stable on the left. Makes sense? And so what everyone's done is then they've got OKM, they used to do it with monkeys, so they can put brains at the same time. You know, pretty much every animal you can think of has been subjected to this, including in humans. And what they do is they take, what would you do? So they get this, I mean, you've got this messy waveform, what are you going to do? But what everybody does is, well, we're going to get a number out of it, right? Some kind of average or something like that. So what you do, you get a big computer, you find all those quick phases, those saccades, get rid of them, right? Then look at the slow phases, and then you average them together, and that's your response, and that's your measure. I expect most of you do the same thing, right? So that's what people have been doing for half a century. And then, of course, by doing that, you've only got an average. Then you say, right, and the metaphor is this. You've got a stimulus, which is the black and white stripes moving at a certain speed. That's the input to this brain, which is this, it's more than a brain, we do know the circuitry. And that then generates high velocity. Of course, when your eye moves, the image moves. So it's feedbacking. It has to be feedback. You can't avoid it. So that feedback comes back, and so that's the circuit. And then if you're a good old engineer, you do what every engineer does, is say, right, I'll measure the input and output ratio and call it gain, and that's what you do. And that's what happens. That's what we've done so many times. And that's what you do. Now, if you want to publish a paper doing something else, you won't get it published, because that's what everybody does. That is the gold standard, right? Fortunately for us, we weren't interested in that. We really wanted to know the detail. Fortunately for us, the people who did this, either they're dead or they're retired. All right? Next slide. We can move on. All right? So we started looking. We're still a lot of people out there. There's still a big zeitgeist of all this stuff, but at least the main protagonists are around. So here we go. So the first thing we looked at is we plotted it out. Absolutely crucial. Plot it out. I should say I do a lot of MATLABing program, but for me, most of my time MATLABing is making programs that plot data out to visualize it. That's what MATLAB's brilliant for. You can do lots of nice things too, but plotting is one of the big things. Learn the plot function, the plot three dimensions, and surf and mesh and all these lovely functions that let you visualize the data. Visualization is what it is. Anyway, you can visualize this as long as you like, and you can notice that it's random, it's a bit of a sorted waveform. And this is, if you look at different people, different times, you get different, they look similar, but it's not quite the same. So we thought, well, what's going on then? So here comes the nitty-gritty stuff, right? Well, what are you going to do? You've got to measure something, so we measure it. So Jonathan spent a long time getting a computer program to measure those slow phases and those quick phases. Measure where they start, how long they take. So we got positions and start positions and time, how far they move. We got all these variables. We pretty much got them all. We did assume it was linear, which most of them really are, and that's when we just got these parameters. Alright, so no one's done this. I mean, I know it sounds silly, but actually no one has done that. Anyway, Jonathan did that. You learned that the hard way. And then we got, right, we've got all these numbers. Well, let's see if they're correlated. Hey, that's what we do, isn't it? We're all psychologists, we like to do PSR. We don't. We do a correlation matrix. So this is a correlation matrix. You've seen this on your SPSS output. We just do it like that. It's just quicker. And you find that you get a correlation matrix. Then you find that this person has a correlation matrix, which is different. That's just telling you the correlation between, say, the start position and the amplitude of the quick phase, minus 0.5 for this one, is minus 0.25, and it varies for everybody. Which is, of course, non-godicity, right? You take this sample and this sample, they have different statistics. That's it. It's not just different means and variances, which are used to. It's different correlation matrix. So, and if you plot them against each other, you get a mess. And everybody's slightly different, some are more different than others, but it's not random. There is relationship there, as you can see from the correlation matrix. But what do you do with it? Well, Jonathan was getting a bit panicky looking into his second year of his PhD. He managed to get the experiments to work, which is no, he did make a few mistakes. I'll say we. And then, Ruth, what are we going to do with all this data tonight? So, somewhere in the back of our brains was this toolbox, and in one of them is called Principal Components Analysis. You've heard of it, PCA? Right? It's all about visualizing data. Now, psychologists love it because it's a way of reducing the degrees of freedom, etc. We weren't interested. We purely wanted to visualize it. There are the engineers in the room who have heard of ARIMA and all those methods. They're complicated. This is really complicated. So, let's look at PCA, Principal Components Analysis, which is just taking data and rotating it in space and aligning it with maximum variance. So here you go. So, for example, here's your data. You align your axes with the data. Mathematically, it's not hard, but it's not trivial either. But you can do it. And SPS can do it. And more to the point, MATLAB can do it. My set of functions. So then, you do this. So here's the same one again. You look at you see they are very different. And then you do principal components analysis, you rotate them, and you find that actually there aren't many degrees of freedom here. There's only 3 in this case. So you get 3 factors. Now, if you don't know PCA, don't worry. This is not an exercise on PCA, but the point is that you found there's 3 dimensions, and you can plot how your original data works in those 3 dimensions, and these are called loading factors, and the point is that they are quite similar, but in different orders. Light bulb goes on. For mathematicians, that's the eigenvalues are different, but the eigenvectors are the same. So these subjects of ours are doing different things, it's just that the dimensions have different noise in them. So, that's interesting. So, that encouraged Jonathan. Let's do the next thing. So now, we do the same thing. We've got all those vectors, all those measurements for every cycle of this Agnes, and then we look at it, not do we correlate them between each other, but we correlate them with each other backwards in time as well. And we played around with it, but here's 4 cycles. Now, I'm not going through the math. It turns out there are 13 degrees of freedom, 13 dimensions, which is more than possibly thinking. And we plotted them all out, and suddenly, this is one of those eureka moments you hear about. It actually does happen. And we suddenly got, now it wasn't obvious at first because this is all jumbled up. But I thought, hey, look, there's some similarity here. So we had to write another program. Poor John, he's so good about that now. And we could do it by hand, but a computer did it quicker in the end. And we found that we could order all of these eigenvectors into these patterns. It's the same thing being displaced by one. What on earth is all that telling us? It's telling us that what you do on this cycle depends what you do on the last cycle, but not on the previous one. All right? What we call a first order Markov. So absolutely. So John plunked that on his wall, and it was there for about 2 years. He was so amazed by it. Because no one's ever done this, no one's ever looked for it. One didn't even look for it, it just came out of the data. It's like God telling us that, you know what I mean? Weird. So anyway, here comes the math. Don't worry about the equations, but it allowed us to make some mathematical equations of what we thought was going on. And that's what we did. You could do all sorts of lovely stuff, and you do linear algebra with love this and brilliant stuff. But it worked. So then we thought, right, we can simulate this. So here we did. So we just put random numbers in through those equations, and that's the model, call it the model, on the simulations on the right, and the data on the not exactly the same, but conventionally the same. And that's for one of those flows. That's the other lot, the other lot. So we had 3. Oh yes, and then if you plot them all out, that's what I showed you before, and that's the typical person through the same kind of messy, but not completely random relationship. So, why hasn't anyone done this? Because they're stuck in that negative, right? So, get rid of it. And then you find out that that's what's going on. So we now understand that, and I should say, let me just go back a minute. For those of you who do computational people, those equations tell us something very different from what we'd ever expected, which is these are equations of a simple adaptive process. They're exactly a learning equation. The brain is learning 3 things at the same time. So it's not a response, it's not a reflexive response at all. The brain is trying to learn at what speed to make it, but if it goes too fast, then the quick phases are too big because you can't see anything during this account. So it's balancing all these things out, and that's what we have. So that, and of course that must be going on in that boy's brain as well. So what's the lessons? Well, first of all, check out this. Well, you've got to recognize it's a metaphor, right? Which we could, because I've got a brain full of stuff, try to get rid of it. So we just explore, let's have a look. Let's just have a look at it. That's all we do. There's no hypothesis, right? Absolutely, definitely no hypothesis. The results we got, it's purely the data telling us, is that it's unexpected, and these 3 equations explain pretty much everything, stochastically. What was the key thing? Transformation of the data in 13 dimensions, rotating it, which you can do easily. We didn't chuck out the degrees of freedom like all the psychologists do with a scree plot and pull out the first 3, all that stuff. And the other thing I have to say was, looking back, it's easy now. You could write that program in no time at all and do it all. It took a long time to start. And he got his PhD. And he published a couple of papers, another one on the way, and he got a job. Right? And now he works over an external West Foundation trying to help children with learning difficulties using some of these. If you'd asked me 2 years ago about what was going on, no idea. So that is pure exploration, and it paid off. You could say it doesn't always pay off.
Quite a provocative question. If this was all about adaptive and learning,
Yeah.
why did the brain never learn? Why does it keep going through this process? Why has it never reached a stage?
Well, in this experiment, because we're making it do that, because the world's moving, you've got to follow it. But how you follow that is complicated.
But why does it never work out the rules?
Because it's conflating itself. Because there's noise. So if you follow it very accurately, then you need to move back to look at where you... If I said follow a point of light, you will follow it. If I say look at this... So when I walk through the world like this, right, then I could follow one person as I walk, but because I know where I'm going. So when I'm walking, I need to keep looking ahead. So that means I've got to keep moving my eyes. I've got to follow it to see it, but if I see it, I can't see where I'm going, so I've got to come back again. So there's conflict, and it's noisy, stochastic, and that's what's happening. Now, why that young man has nystagmus, we don't still know, but now we know that these slow phases and quick phases are now highly correlated, and we've got a model of how that might work. So that's yet to come. But the point is that if we stuck to a metaphor, we never see that. All right? So does that answer your question? Kind of.
Kind of.
I'll answer it better later. Right, let's talk about something you know more about. But that's Simon. So now you're making those saccades, your brain, your superior colliculus, your frontal eye fields are all firing like crazy, making this stuff. You don't know it's happening. It doesn't mean it's not happening. It's happening. You're just not conscious of it. What is happening? So here's something that you're a bit more conscious of, perhaps. Reaction times. Every psychologist, all of you who've done reaction time, the most boring experiments you can imagine. You sit there, press a button, and light comes in. Right? And it's been studied since 1865-ish. Helmholtz, Donders were the first. Wundt, famous father of psychology, studied everyone studied it, and continue to. But my concern is that this is getting a bit of a problem with computer metaphor. Because the way most people think of reaction time is passing out pieces of time, right? Sit there, warning light comes on, that target comes on, make a movement, make a decision, then of course you've got to make a movement because it's pressing a button, so you've got to move in time. Then you go back to start it again, and so on. So there's all these bits of time, and the kind of default idea is like a computer programmer going, okay, is it on? No, wait, yes, jump here, and so on. And all these bits are kind of independent pieces of time. And that's the kind of default model. I wouldn't say everybody, but most people do. And there are obviously different models for reaction time, but by far the most popular model is the diffusion process. So the idea is, just rewind. You look at a light comes on, and you've got to press a button. And it could be simple reaction times, meaning as soon as it comes on, press a button. Or it could be a choice reaction time. If it comes on the left, press the left button. If it comes on the right, press the right button. They are very different, actually. But nevertheless, the general idea is this is what's happening. So some signal, a light comes on, your brain starts doing a little bit of Bayesian arithmetic, right? And it gets more and more information. The more information you get, the more likely you're sure the light's come off. And you get to some threshold and say, yep, I've reached my alpha point of whatever it is in your head, and you press the button. Because every time you do it, you get a slightly different result because of different kind of information. So it's quite stochastic. So when you get to this internal threshold in your brain, you press the button, and we as experimenters measure that duration of that time, and we plot it out in a distribution, and it always looks a bit like that. Positively skewed, you've all seen it? So quite skewed, and the idea is, the general idea is that this skewness becomes because of this stochasticity. This is modeled by Ratcliffe. He only published about 200 papers on the subject. He owns it. Don't watch it as a reviewer. You're going to like what you have to say. You've got to be careful with who you ask as a reviewer. But there's a colleague of mine. So there's acres of paper. Right? There's a colleague of mine called Roger Carpenter. He was a nice guy. He lives in Cambridge, and he studies saccadic eye movements. bit of a common theme there. Now what he does is he looks at, he has a different method. He thinks, I should say, if you do the mathematics on this, it has what's called an inverse Gaussian distribution. Get that in a second. He says it's not, it's a reciprocal normal distribution, 1 over a normal distribution. And he says what really happens is that you start at the beginning of the trial, some signal on trial 1 reaches some threshold, and then the next trial it reaches the same threshold but at a different speed. And this is distributed, the normal distribution, and you get something that looks like that. Okay? And that's the inverse Gaussian, that's the reciprocal normal. They look very similar. They're not, as I'll get to in a second, but it's really hard to tell from data. These tails are different, but remember the probability of getting those is quite low. So in a normal amount of data, you will not see many tails. So it's hard to tell. So you think, and of course, they don't talk to each other. Right? He said, it's reciprocal normal. No, it's not. It's inverse Gaussian. No, it's not. And actually, what Roger's done now, recently, he's come out with a paper that says, well, it's a bit of that and a bit of that. So, what are you going to do? You can't do, you can do schemas and kurtosis and all that stuff, right? But it doesn't tell you. That yellow bars are that so huge, you can't tell. You can fit your data, don't get me wrong. You can always reject your null hypothesis. But it doesn't really tell you which hypothesis is the correct one. However, the miracle of transformation, what can you do? The answer is absolutely obvious. You look at the reciprocal of the reaction time. If you look at the reciprocal, 1 over, so you've got all these reaction times, you can do this at home, it's easy, take 1 over it, and then plot the distributions, you end up with this. This is the reciprocal inverse Gaussian, this is a complicated formula. And of course it's a reciprocal normal, reciprocal is back to where you started from. So the reciprocal normal is a normal. It's a normal. It can be truncated, which is a tricky problem, I don't want to get into that now. So if you take the reciprocal of your reaction time data, what should you get? Well, it's the acid test, isn't it? No, I'm not doing any hypothesis test, I'm just looking to see what's going on. So there's a Jonathan again. He sat there and did a whole 2,000 of his trials, which is extraordinarily boring. And here's the reaction times in the time domain, and you can see the skewedness here. If you go into 1 over it, which I call rate, 1 over times rate, you end up with a symmetrical distribution. It's a bit normal-ish, actually. Okay? So, oh, gosh, Roger must be right. Whoa. Well, don't want to meet Radcliffe, he's not going to be very happy with it. But there's something worrying about this. Really deeply worrying. If this is right, and you know something about normal distribution, it never stops. There's no end to it. It's infinitely. It's over the infinite line. So, and it turns out that the reciprocal normal distribution does not have a mean. It doesn't have variance, doesn't have skewness. You can measure it. You can do the number crunching, that will do it for you. But it doesn't mean anything. It does not have a finite, it has an infinite mean. And the reason is, because if you wait long enough, you're going to get an outlier. That outlier is so far out there that it moves the mean. It doesn't have a mean, which is kind of mind-boggling. How can you think they don't have a mean? Well, they don't. There's a whole set of. So we published a paper to explain that. It does not have a mean, and the reason is this. So imagine we had a reciprocal normal for this distribution, and we measured its mean, and we waited longer and longer, and kept doing more and more trials. What happens to the mean is it slowly creeps up forever and ever and ever. It never flattens out. Is that crazy or what? So, of course, you only do a certain experiment at a certain time, right? But what it means is the results you get depends on how long you did the experiment. So if you did your experiment and you had a timeout of 20 seconds, you have a higher mean than if you did in 10 seconds. It's worse than that, of course, because what do all psychologists do? Sorry, psychologists. Is you check out the outliers, you do a log transformation, get it to do look at normal-ish, then put it into SPSS, right? That's what everyone does. And of course, they're chucking the baby out of the farm. So if you really want to transform data, just reciprocally, okay? And you've got normal distribution. So we did another experiment, we did it again. Never mind that. But we collected lots of people and we plotted it carefully. This is under review at the moment, and this is what we get when we merge lots of people together to get enough data sets. It's very, very close to one. To check that we've done all our analysis right, we Monte Carlo. It's really important to do this. We put random numbers in to see what happens to all that analysis we've done. And we put a real, true reciprocal normal in, and it really is something. So we know the analysis works. If you put in the inverse Gaussian, that's how the model, it doesn't work. And these are probability things. So it's not perfect, so it would fail a significance test. But who cares? It's normal. Very, very close to normal. So why would it be normal? Well, that's the big question. We don't really know. Roger's idea, I don't believe. There's something going on. All right, so go back down a minute. Now, what's the other assumption? Everybody has done this. It's assumed that when you press that button, the time taken is independent of the previous time. Well, it's not true. Totally untrue. If you look at a block of data, you find that the reaction time decreases quite quickly over the first 5 or so trials, and then levels off. If you look at it in the rate domain, upside down, it increases. So they're not stationary, nor independent. So then you have to go into your toolbox. What on earth, how do we get to the bottom of this? So in amongst your toolbox, you find a thing called partial autocorrelation. Well, first of all, you find autocorrelation. You think, so I can look at the autocorrelation. Is this reaction time correlated to that one? Yeah, it is. But if it is correlated to that one, it must be correlated to the previous one, because that one's correlated to that one. So because of its correlation is going to just go on. It's going to find a particular pattern. So we don't want that. What we want to know is this reaction time on the nth trial correlated with n-1, n-2 separately? And the answer is, and the only way you can do that is partial autocorrelation. And the answer is, yeah, it is. Partial autocorrelation functions lagged. I know it's getting complicated, but I got all this data, all these trials, and I just correlate. I just shift them by 1 lag, correlate them, shift them by 2 lag, and take out the correlation that you've got for the previous for 1 lag. And you find you do get this. Of course, you're never sure if you've done all this math lagging right. So what do? You shuffle up all the data and do the whole thing again. And there's no autocorrelation. So it's genuine. It's in the data. It's a mistake. I'm always worried about making a mistake. Now, I'm not going to go into all the detail here, but you can actually estimate those correlations. These correlations themselves are bias estimators. But you can do that. And what we find is this. That your response, or I should say, you can only do this in the rate domain because the study is normally distributed. You can't do it in the time domain. And you find that actually there's about your reaction time on this trial, or your reaction rate, one over that, it depends on the previous 3 trials. So what we've done now depends on what you did last trial, the previous trial, the previous trial. No one's done it, but why not? I don't know, assumed independence, I suppose. And you turn the whole thing upside down. I'm whizzing through this bit. And what you find is, what's the effect of this memory? It shifts your distribution to one. It actually shifts your distribution. Now, that's where we are. We've got this published. Well, it's not published. I'm hopeful. But what it seems is that your memory of what you've done before is used to move around your rate of response. It's the rate of response, not the reaction time. Our brains aren't operating in time domain.
So does this mean that when you're doing always the same task that you get faster in your reaction until something happens which you're not expecting then?
To some extent, yes.
So could you say the brain is already starting early before it's detecting that something is happening and it's saying, okay, it's the same again and going to the reaction?
It could be.
And then if something is different, it takes longer to really sort out what it is?
No, oddly enough. It seems peculiarity, at least in these experiments, this kind of experiment, that if you repeat what you've done, well, you're asking a really difficult question, but the answer is, is that if you repeat it, you get a faster reaction time. If you alternate it, so this is only left-right, so you have left, 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 you will find, it's random, you get faster and faster. But if it goes left, right, left, right, left, right, left, right, left, right, you also go faster. It's extracting a pattern now, which is...
Yeah, maintain anyways. If you change suddenly the pattern, then there's...
then the reaction time goes up. Yeah.
Okay, because that's the thing which also people are doing error potentials, and they say it's earlier, it's later, and I think there's also that defect inside. That would be an argument for it.
Possibly. We'll talk about that further, because that's a very interesting point, because this is in the time domain, not in the space domain. So in real life, of course, you've got lots of choices occurring in time. So what we don't know is how that's parceled out. But this leads to a hypothesis. Hey, you make me feel more comfortable. We have a hypothesis now. Why should this be the case? And we think it's because the rate. We want to operate in the rate domain, not the time domain. I know it's counterintuitive, but think about it like a rat pressing a lever. Yes, like a skimmer box, right? Presses the lever, it's a food, presses the lever. It's not making a decision on it. What the rat's trying to do is maximize the rate of reward, how much food can get over time, not just on a single trial. So, this is a hypothesis, it definitely is, and what we're saying is there is an optimum time to respond. And so every trial is different, so you get the normal distribution in the rate domain, not in the time domain. And that is really interesting. Why is it really interesting? I'm just going to go a bit, is that right? How much time I have actually? Right. That's really interesting. But not the second one. Final. I'm going to jump a bit. I want you to look at this. I have no idea what's going on. I really don't. Game theory. We've all heard of game theory. Right? Well, you're thinking what I'm thinking, what you're thinking, I'm thinking. If you're going to do that, I'm going to do that. But if you don't do that, then I better do that. Right? So this is Nash equilibrium. Game theory, what to do with it. We're at the moment, actually, aren't we? We're in Ukraine. So the point is that the extrapolation from the decision making, of course, is in real life you have to make decisions in a context with other people who might be on your side or not on your side. In biology, it comes from foraging. That's the main goal, the idea that animals foraging, if they inherit this particular strategy, called an evolution stable strategy, they all have the same strategy, they're all going to go for the same piece of food and they're not going to get anything. Right? So you need some way around that, and the idea is that you might randomize. If I behave randomly, I know what I'm going to do. You can't know what I'm going to do. So it might be that'd be better. So the whole thing about game theory is that is there a strategy that I can adopt which maximizes my reward regardless of what you do? Or knowing that you're going to do the same thing. Right? Now that's what Nash did, famous guy. But because we're talking about iterative games, because then you have to play these games. If you play lots of games, I get to learn a bit about what you do. So that's the idea. So that's decision making in a game theoretic approach. And of course it's been studied hugely in sociology. So we thought, well, we better look at this because there's something going on. Our previous work suggested that at rate, you might go for the choices that give you more, in proportion to the amount of reward, which is called the matching. So I'll jump straight to it. So here's an experiment. You've got 3 buttons to press. One's called 12, one's called 6, one's called 4. And we're playing one player against one player. And we have discrete trials where we play trial 1, we press a button each, then trial 2, so. And if I press 12 and you press some other button, I get 12 points. Reward 12. If you press 12 and I press 12, we both get nothing. Right? If you both press 6, we get press 4, we get nothing. Otherwise, if you press different, you get whatever it says. And to make this we talked about this last night, but to make it as real as you possibly could and get ethics for it, our students got chocolate in proportion to the number of points, which is a bit peculiar, but we could think of no way of motivating them. They really did get chocolate. We had to, in fact, we had to change it around because they were doing so well, we don't have chocolate. So we had to change it. But anyway, so they got in proportion to what they got. So now, let's think about this. What would you do? So, you think, well, if I press 12 every time, I'm going to get more chocolate. But you're doing the same thing. And I shouldn't press. If I press 6, then you press 12. But at least I might get it. But you might be thinking the same thing. Now, the idea we weren't competing. This wasn't, can I get more chocolate than you? Can I get as much chocolate as I want? Would like, right? And I'm also full. I hit 3 buttons for a really good reason. Because when you do the Nash equilibria, which is find the optimal strategy, you find that there are 2 optimal strategies. One of the strategies, if you're player 1 and I'm player 2, is you press 12 and I press 6. All the time. Or you press 6 and I press 12. Right? You can work it out. That's the best of it. The really important point is there's never a reason to press button 4. Why would I ever want to press 4? If I press 6, like you can only press 1 button, so it's going to be a 12 or a 6. So we got to negotiate over 12 and 6. We're never going to press 4. Alright? Does that make sense? Why would you ever press 4? So we thought, okay, we were quite, my interest was in, will people press 4, and 6 and 12 in proportion to the amount of reward they would get? Whilst Mr. Nash would say, you do one of these. Pursue a Nash equilibrium. Contentious though it might be, because we were both fighting. So we did the experiment. We had 15 pairs of students, and they did the same thing. They knew what the total was every trial, but they didn't know what the other person got. So they weren't competing. They had no idea what the other person. They knew if they got 0, that the other person must have pressed their same button. So what happened? Well, so I did just like you would do. On the psychology cap on and my little SPSS thing on, and do what everyone would do, which is group all the data together and have a look. Makes sense. And out of 15 pairs, they had two whole rounds each. So they did it again, second time, just to see if they learned everything. So it meant this is the first round, we had nearly 1,500 trials, I think on 2 trials, so I need to press a button or something. And this is how it distributed itself. So player 1 pressed 4 this time, 10. These are the combinations that people did. Notice they like to press 12s and 6s. Press 4. They press 4. Well, infinite. Pressed it quite a few times. So what do you do? Well, do a chi-square test of independence, etc., and of course it's highly significant. You can easily see that on average, people what they did depended on what the other person did. And it depended on what the other person did in the previous trial, and it depended on what they did on their previous trial. So you do the marginals, and you can plot things out, and probably the pressing a button in proportion to their reward. Well, it doesn't really follow quite what I expected, but it's not. It's interesting. Right. I would have thought they would press 4, where a Nash equilibrium said you wouldn't. So they pressed 4 button, a lot less than you would predict. But the other 2 were in a straight line, so ambiguous. And then, what do you do next? Well, this is what we did. So, sorry. One thing we've forgotten to do is to look at our data. Right? Bunch it all together like we always did, right? So let's throw all that away. That was a waste of time. Let's look at our data in reality. And make a MATLAB program to plot all that in just the way you can see it. So blue means press 12, green, press 6, yellow means press 4, which is not here on this one. And that's trial number, and that's player 1, player 2, that's the first round of play, that's the second round. And now you can see exactly what's happening here. If it's red and they press the same button. Okay, follow me so far? So this pair were pretty close to a Nash equilibrium, right? They're optimized. One press 12, one press 6. And he or she got 282 Smarties and got 187. So that's pretty good going, actually. A few contentions, but not much. And they kept the same strategy the same time. Then, and we looked at this, and okay, so a few yellow buttons there, a few 4s. They're obviously jumping a little bit to start with, but they've done pretty well, right? So we thought, oh, right. Okay, this is Nash, he's right. Good old Nash. Then keep looking over them, looking over them. And then you start seeing stuff going a bit wonky here. What's going on? So it starts off being a bit random and then settles down to a strategy. So they're fighting it out somehow. But then, if I whisk through, they get really random. Look at this. Totally pressing 4 all the time. Lots of red, and their scores are low. So it's a completely different strategy. Which you would never see if you didn't look at the individual games. And the final one, I think, is this one. They cooperated. Press 12 on this. Of course, that's not supposed to do that. So the point really I'm trying to make is that I have absolutely no idea. If anyone's got an idea what to do next, I'm very interested. But it seems that people they're not ergodic in the slightest. We're talking about cognitive styles. I don't know. So these are couples of people playing against each other, not couples, they're people, they're pairs of players. And sometimes they've got a Nash kind of equilibrium, still fighting it out. Others just go random, and they press forward quite a lot. And as I think this lot, they even cooperate. They still didn't do very well, so their cooperation didn't get them as much as they thought it would. But there you go. So we know I've got another lot of students coming up this next year, and they're going to look at what we're going to do next. Don't tell them, because you have to see them, is that they're going to play again, but they're going to play against the computer, but not knowing what they can do. So we're going to get the computer to adopt a strategy to see if the other player will change their strategy according to that. At the moment, we don't know who's doing what. Right? And then, that's one lot of experiments, but I'm absolutely curious to see what goes on. And the other experiment is we're going to have 10 players playing again. How do you compete with 10? I don't know. So that's the other thing. So anyway, so I'm going to stop now. I'm going to get falling asleep, which is lunch. The point I'm trying to make is look at your data. Fiddle around with it. You can spend all your time looking at data. That's the important thing. Doing statistics, it's just wrapping up time. That's not what it's about. It's not about standardized effects. It's about effect. Things happen. And that's the moral of the story I'm trying to get across. So step out of your metaphor, step out of the box, and think. Do something. Right. There you go.